Hello friends! In the previous video, we have seen conditional statements. This is generally the most confusing of all logical connectives if you are not familiar with it. Let's go into some details about it so that we can grasp it more clearly. Remember that a conditional statement is in the form if P, then Q. And here, P is the premise and Q is the conclusion. This statement simply says that the conclusion is true under the condition that the premise is true. Only case that it is false is when the premise is true but the conclusion is false. To understand this, consider P as a set that is contained in another larger set called Q. Inside the set P is the region for which P is true, and outside the set P is the region for which P is false. Similarly, inside the set Q is the region for which Q is true, and outside the set Q is the region for which Q is false. A true conditional statement is like this illustration. If P is true, Q is true. That is why we say that Q is true whenever P is true. P is sufficient for Q because there is no region for which P is true but Q is false. P only if Q, because P cannot be true if Q is false. In the figure, notice that when P is false, there are regions where Q is true and regions where Q is false. This means that if P is false, we cannot say confidently anything about the truth of Q. That's why we assume the conditional statement is true when premise is false. Because Q may be true or false in this case. This is the rationale behind why we say Q is a necessary condition for P. Q is a necessary but not sufficient condition for P on its own, as there are some regions where Q is true but P is false. Now suppose we have a figure like this. There is a region in which P is true but Q is false. Then if P then Q statement will be false, as P does not guarantee or it's not sufficient for Q. To make these sets more concrete, let's consider the following statement. If an integer is divisible by 6, then it's also divisible by 3. Here P is if an integer is divisible by 6, and Q is it's also divisible by 3. We clearly see that this is a true statement. Here P can be considered as the set of all integers divisible by 6, and Q as the set of all integers divisible by 3. We know that Q contains P, so being divisible by 6 is sufficient for being divisible by 3. Being divisible by 3 is necessary condition for being divisible by 6, because there are multiples of 3 that is not divisible by 6, like 9 and 15. On the other hand, converse of this statement, which is if a number is divisible by 3, then it's also divisible by 6, is false, because there are numbers divisible by 3 but not divisible by 6. So, premise is not sufficient for conclusion in the converse of the original statement.